Hello, good morning. Myself, Dr. Shaila Dinkar. We'll continue with FIR filter design in this video. We'll discuss frequency sampling method in particular. This is the book that I have published with Wiley. You can go through the book for further details. We have already considered Fourier series expansion method, wherein what we do is we consider the brick wall response, that is complete ideal response in the frequency domain, and then we go on designing the filter impulse response in time domain. We revert in the time domain and then go ahead by adjusting the response in the time domain. Now, in case of frequency sampling method, this is a direct digital design. We will go in the time domain after properly selecting the points in the frequency domain. So you can consider this as the first step in the adaptive filter design. What we'll do is we will specify the corresponding response of the filter in frequency domain. For that, we select frequency points as the desired response. And these frequency points are considered for the desired response, considering that there may be some small ripple in the passband and there will be some oscillations in the stopband as well. So the basic process involved can be described as follows. The user specifies the desired specifications for the filter, namely the frequency response characteristics, that is obviously in the frequency domain. The designer will then select proper frequency points by appropriately sampling the frequency response in the frequency domain using a sampling theorem in frequency domain. What the sampling theorem says, the number of frequency points those we are sampling should be greater than or equal to number of points in the impulse response of the filter in the time domain. So the number of frequency points selected must be greater than the number of points in the unit sample response or the required order of the filter, right? So if the impulse response of the filter needs 10 points, the frequency points must be greater than 10. Now what we do after selecting the frequency points? These selected frequency points will then be considered as DFT coefficients. And to revert back in the time domain, what we do, we take IDFT. And then we can get the IDFT as the impulse response of the desired filter. The impulse response will then be Z transformed to get the transfer function in the Z domain so that we can check whether the corresponding filter is remaining stable or not. And the phase response we will have to select. How to select the phase response so that it will be linear, and that is the desired phase response for the FIR filter. So we'll have to select the proper phase response in order that it satisfies the linearity. At frequencies other than the sampling points, discrete time filters so obtained will provide the interpolation between the adjacent frequencies. So interpolation for in-between points will be there, and at the selected points you will get the desired response that you expect. Now what is the process? Now we know that the sample signal has a Fourier transform, that is continuous transform, called as DTFT. So if I consider that the impulse response of the filter is a discrete time signal, if we want to get the frequency domain picture of it, how it will be? It will be a continuous transform. It will be called a discrete time Fourier transform. That is called a DTFT. Now, this discrete time Fourier transform has some properties. The main property is that it is periodic with period equal to 2 pi. So what we may do, we may consider the spectrum over one period of it and then sample to get the DFT points. So what we do? Let us consider that Hn represents the impulse response of the filter with capital N points. And as we are saying, the corresponding Hn will be the corresponding DFT coefficient and must also be equal to n in number, because it has to be greater than or equal to the number of points in the impulse response. H of n is the magnitude of the DFT and psi of n is the phase. If we say this, then we can write Hn, that is the DFT coefficients as magnitude response, and e raised to j psi n, where psi n is the phase response. Now what we do? We take IDFT. So these are the DFT coefficients. Now we take IDFT. So we get HM inverse DFT as 1 upon n summation n varying from n minus 1 h of n w n raised to nm. Now this is as per the IDFT formula, where what is w is e raised to minus j2 pi by capital N, and this h of n is the corresponding DFT coefficients. Okay. now what we'll have to do, we'll have to take the transfer function in the z domain for this HM. So what will be Hz? Hz is summation m varying from 0 to n minus 1 hm z raised to minus m. So we just put the value of hm over here using the inverse DFT. So we get Hn summation wn raised to minus w capital N is the base raised to minus n, z raised to minus 1 raised to m, by putting the value of hm in the equation. And then what we do? We just take the closed form expression for this summation. So it is 1 minus z raised to minus n divided into w raised to nm divided by 1 minus z inverse w raised to n. This is a closed form expression for this summation. Then what we do? We just write the value of z, and we also write the value of w. W is e raised to minus j 2 pi by capital N, and z is e raised to minus j omega t. Right. So after putting the value of um, z and w, we get this equation. Then if we want to calculate the corresponding frequency response, we'll have to write hz as h omega, where we will be calculating the corresponding response with respect to omega, and here it is e raised to minus j omega t. So this omega we have already substituted. So this omega, h omega, is the corresponding frequency response. So h of omega can be written as hn. Now this summation we will write it as sine n omega t minus 2 pi n upon capital N divided by 2 divided by sine omega t minus 2 pi n divided by n by 2, and 0 is varying, m is varying from 0 to n minus 1. Now what we have actually done is we have just written this particular expression in the form of, we have taken one e raised to minus j n w n minus 2 pi n by capital N by 2 as a common factor, and then we wrote it as sine theta upon theta. We want to express it in the form of sine theta upon theta. So this will be you can say simplified. And how it would look like, we can select the phase response also as shown, so that the phase is linear. So what we do, we select sine is equal to minus of n minus 1 and pi upon n. So if sine is directly proportional to n, it has linear phase. So our purpose is solved in this case. Let me illustrate this using one simple example. Design 11 coefficient FIR low pass filter using frequency sampling method with cutoff frequency of twice fs by 11, where fs is the sampling frequency. Plot the magnitude response of the resulting filter. So let us see how the design will be carried out and what will be the response. Now we are considering capital N is equal to 11. So the fundamental DFT frequency will be fs by 11. So it will be fs by 11, 2fs by 11, 3fs by 11. Those are the selected frequency points. The cutoff frequency of 2fs by 11 will occur at n is equal to 2, obviously. Now we'll select the magnitude response and phase response. Magnitude response is equal to 1 for n equal to 1, 2 and 9, 10, because it will be symmetrical, and equal to 0 for n is equal to 3 to 8. And then sine is equal to minus 10 n pi upon 11, because this is n minus 1, so it becomes 10 in this case. Now let h0 is equal to 1, that is at 0 the corresponding response will be equal to 1. So Hn can be written as e raised to minus j 10 pi n pi upon 10 n pi upon 11 for 0, 1, 2, and similarly for 9, 10, if we consider the response between 0 to 2 pi, and then equal to 0 for n is equal to 3 to 8. Okay. So these are the DFT coefficients. Now we take the inverse DFT to obtain HM. HM will be equal to 1 upon n. Then I will write 1 plus summation twice the real part of this into this 2 pi k m upon 11. This is directly using the formula. So accordingly, we'll substitute for h of 0. So when I substitute n is equal to 0, I will get this coefficient. Then I substitute n is equal to 1 to get h1. N is equal to 2, 3, 4, 5. So I will evaluate these coefficients, right? Now h of 4 will be same as h of 6, h of 3 will be same as h of 7, h of 2 will be same as h of 8, h of 1 will be same as h9, and h of 0 will be same as h10. These are the corresponding coefficients because the response will be symmetrical. Then we'll have to write the MATLAB code to find the frequency response, that is h omega. And when we plot this response, we get this corresponding response for the low pass filter. Now, in this case, we have considered h0 is equal to 1, then h1. Now, corresponding sampling frequency. What is the sampling frequency? Sampling frequency is, let us say, 1000. So, in that case, what will be the corresponding case? The corresponding values here, n2, we are considering n is equal to 1, it is equal to 1, n is equal to 2, it is 1, and same response will appear up to 2 pi. Is that right? So for 9, 10, again it will be equal to 1. So this is how we are getting the desired response. And during the pass band, the corresponding phase is linear, which is required.